Okay, so I'm going to get started. Today's announcements are that you guys have quiz number 3 this week in recitation. And so that's always going to cover everything up through Friday the week before. So most of chapter 5 and 4 is going to be on there, or at least fair game for the quiz, except for polymerization, which is the last bit of chapter 5 I haven't covered. And then since we're finishing chapter 5 today, I'm going to set the due date on the homework for next Monday at 9 a.m. And I guess just as a reminder, we have an exam a little over a week from today, so Tuesday night next week. So I'll open up the homework for chapter 6 as well today, so you can get in there and start working on it. Okay, any questions about that? Okay, cool. So I realized after class ended that there were a couple more things that I did want to say about radical HBr addition. So I'm just going to summarize that a little bit real quick for people who missed it before I move on. Okay, so we went through the mechanism. Because we're looking at a radical chain reaction here, it goes a little bit differently than the regular two electron arrow pushing we've seen before. We break the steps down into initiation, propagation, termination. Real quick, I'm going to write the whole thing. You know what? No. Let's take unnecessary time. But I guess, so you remember I wrote down initiation steps, propagation steps, and termination steps. One thing I didn't emphasize is that propagation is what should be giving you the major products. So if you remember, when we did propagation, maybe I'll draw out those steps real quick. So we start propagation with the Br dot that we produce during initiation. We do that 3-arrow fishhook kind of thing that is real common for when we're reacting a radical with a non-radical. We end up making a new carbon dot radical, and then we react that with an HBr. Spit out a new Br dot. So a couple of people asked me, couldn't this radical just bump into a Br radical? Why doesn't that happen? And the answer is it does some of the time. That wouldn't be propagation, though. That would be termination, because when you stick two radicals together, they stop being radicals. So you're not continuing the chain cycle if you stick two radicals together. And also, if we want to keep this thing going, we're going to have to reproduce the radical that we started propagation with if we want it to go on and perpetuate the cycle. So also, it's just a lot more likely that one radical is going to bump into a non-radical, given how low the concentration of radicals is at any time. Quite a bit less than 1% of the molecules are actually carrying a radical at any time. Okay, so this should be our major product. And note that for reasons we talked about last time, the radical being happiest in the place where it's most substituted, that's kind of what forces this to go anti-Markovnikov, just because you happen to add the bromine first, and that means the carbon radical wants to be more substituted, and that's ultimately where the H ends up adding. So major product ends up anti-Markovnikov. You'll also end up producing a small amount of the Markovnikov product just because the radical prefers to be here, but there is some % chance it could end up in the wrong location as well. And that's true for all of the regiochemistry we've seen so far, Markovnikov or anti-Markovnikov. That just means that it favors one location over the other, but it doesn't mean it's 100%. There's always going to be a little bit of the wrong one mixed in there. So if you're doing this reaction in a lab, you would never be able to get 100% yield. You might get 90+%, and then the remaining few % of molecules either didn't react at all, or maybe they gave you the wrong product. Okay, so propagation gives you the major product, and then termination also gives you a bunch of minor products. Okay, so the odds of two radicals bumping into each other is always going to be lower than the odds of a radical bumping into a non-radical, so termination is only happening a small % of the time too. Although eventually it'll win out and all your radicals will die. Okay, so questions about any of that so far? Yeah?
So in the termination step, would we have to draw all the possibilities?
Good question. So I guess usually the way I'll set it up, because sometimes there's like, a bunch of different options, I'll say like show 2 example termination steps, and then you can just like pick any 2 combos at random and show those terminating. Yeah. Okay, any other questions about this? Yeah, in the back.
We're asked to identify minor products. Will questions like that specify whether it's in the propagation or the termination step?
It might or it might not. I'm just trying to remember exactly what questions I have on the sapling homework for this chapter. I guess if it doesn't specify, try showing both and see if that does it. Yep. Okay. Cool. So that's pretty much the last little bit I wanted to say about radical HBr addition that I forgot to mention last time. But that's kind of an important thing. Like propagation is happening way more frequently than termination does. Okay, so the last reaction that we're going to see in this chapter is really more like a category of reactions. And we're just seeing a few first examples in this category for now. So what we're going to look at is polymerization. So I guess polymers are a huge, huge field for organic chemistry because a lot of materials that stuff is made of in our modern world is built out of polymers. So like anything made of plastic is a polymer. Also, polymerization plays a huge role in biochemistry too. So like proteins are polymers of amino acids. DNA is a polymer of base pairs. But really, I guess, again, if you look at the name, the parts that it's made of kind of explain what we're talking about here. So poly means many, and mer means part. So polymerization just means we're sticking together many copies, many parts of the same thing. So we're making a long chain of repeat units, basically. Another name for those repeat units, or the molecules that they're made from, is monomers. Which means one parts. So we're sticking together a bunch of single parts into a many-part chain. Okay. So there's actually a ton of different reactions we can do that will link things together into a long chain. But the ones we're going to focus on in this chapter, just as a little bit here, are using alkenes because that's what this chapter is about. There's actually several different ways you can polymerize alkenes too, but we're going to sort of focus on a subfield of that, which is radical initiation, similar to this HBr reaction up here. So we're going to focus on radical alkene polymerization. Okay. So this is actually a real similar kind of reaction setup to what we did for radical HBr addition. Again, because it's a radical chain reaction, we need initiation, propagation, termination. The initiator is usually a little bit different. There's a bunch of choices, and they're all a little more complicated than what we've looked at so far. I'm going to leave it vague and just say usually something to create an R dot radical. So like AIBN that I sort of mentioned last time is one example of that. Would create some R group with a dot on the carbon. Okay. So what can happen here is if you've got just the initiator and the alkene and you don't have any other molecule around like HBr for it to react with, something really cool can happen because you have an R dot here, and I'm just write this out as CH2 to keep it like I have in the notes. So we don't have any HBr for it to go generate a Br dot radical off of. So pretty much our only option is have the radical just go in and react with whatever alkene we got. So again, oh, and this is propagation, sorry, by the way. So again, have the R dot go in, contribute 1 electron to a bond. Alkene pi bond creates, or chips in the other electron, and then the leftover falls back. So we end up with R, CH2, CH2, with a dot on the outermost carbon. All right, so this is pretty much the same arrow pushing as what we saw for HBr radical addition. But we don't have anything for this to go pull a proton off of. There's no HBr for it to pull an H from. So instead, what's going to happen is it's going to bump into another molecule of alkene eventually, and it's going to do the same thing that was done to it. So chip in 1 electron, alkene contributes the other, leftover falls back. And you've added another copy of the alkene onto our suddenly growing chain here. And then this can happen again and again and again and again and again. And eventually, so the way that we show like this step happens a bunch of times, usually is with like staggered arrows, usually like 3 or 4 of them like this. Okay, so that happens many times. And eventually you just get this long chain that's a whole bunch of CH2s together. So the way that we write that is CH2, CH2, because that's kind of our repeat unit. You know what, I'm going to have to move down here, give myself room. So CH2, CH2. And then the bonds that would go on to the next repeat unit on either side, we actually draw a set of parentheses across those bonds. So we're saying, okay, this is our repeat unit. We're going to have a copy here and then next copy like moving along the chain. And then we're going to say N as a subscript. So there's a lot. We don't know exactly how many. There's a way we can sort of measure statistics of like the polymer chain length, but it turns out not all the chains are going to end up getting to the same size before termination ends up happening. Okay. So N here is usually going to be a really huge number, like thousands to millions, depending on what exactly the chemistry setup is that you have. Okay. So eventually, just like it did for HBr addition, 2 radicals might bump into each other. So maybe like 2 chain ends here with a developing radical might stick together, and you'll end up with a chain that's like double length. And that's pretty much the only option they have for killing each other off, actually, unless you end up adding something else to the reaction to stop it. Okay, so questions about that mechanism? Uh-huh. Sorry, what is N limited by? So a lot of things, it turns out. Partially, it turns out like concentration of ethylene, the alkene that we're using here. Like it's sort of a competition between like how fast is propagation compared to how fast is termination. And termination can get more likely, you know, as you start using up all of the alkene in the reaction. But then it turns out you also have to deal with physical properties. Like the longer the polymer chains get, the more viscous the reaction gets. And then the odds of like chains snaking around and sticking their ends together gets lower and lower. And so it's real complicated as it turns out. Yeah, I took like 2 semesters of polymer chemistry when I was an undergrad, and there's a bunch of stuff that you have to take into account. So we're just sort of looking at like the basic mechanism going on here. So. Okay, uh-huh.
You might have just touched on it, but why do the lone electrons on 2 different chains
So it has to do with, that's pretty much the only way to do a termination, which is kind of like the same as it was for HBr addition up here. The only way for everything to get a full octet is for two radicals to join up. So like, I guess here, if you had like some long chain and then you had CH2 at the end, and over here you had some long chain with CH2, eventually maybe they would bump into each other and you just end up with a long chain with the two what used to be terminal radicals sticking together and holding the two ends of the chain together.
So does that mean we should see the R group on both sides of a finished chain?
Yeah. Yeah, so it may be like a tiny infinitesimal like portion of the chain, because depending on how long it gets, maybe there's like a million copies of CH2 and then like one single R group out at the end, at both ends potentially, yeah. There's also some other reactions that can go on that like radical chain transfer and stuff like that, so they might not always have every chain with an R group on it by the time everything's done. But this is kind of like the oldest, simplest way of doing things. So. Okay, so the molecule that I used for this is ethene under IUPAC, or under old school naming ethylene, right? So if I'm linking together a bunch of copies of ethylene, what polymer am I making? Polyethylene. It's that simple. Just throw a poly in front of the name. So, okay. So I got ethylene here. I do a radical initiator. I make polyethylene. If I've got this one, which is an aromatic ring attached to an alkene, we have already seen that aromatic rings don't do any of the alkene chemistry, so think of this as an unreactive lump for the time being. It's just hanging off of the alkene that's actually doing this. This one, as it turns out, is called styrene. So we polymerize that, we're going to get polystyrene. Okay, so to draw this, we're going to have to show we still have the same CH2, or I guess like 2 carbon repeat unit that used to be the alkene, but out of those 2 carbons of the alkene, one still has the aromatic ring attached to it. So we're going to show it polymerizing like this. Okay, so that's polystyrene. Okay, and then I sort of briefly mentioned this earlier when we were looking at alkene naming at the start of chapter 4, I think, but this one is called vinyl chloride, colloquially. Under IUPAC, it's something else, 1-chloroethene, but I guess the polymer names sort of got applied before people got really into IUPAC. Okay, so we polymerize this, and we're going to get, again, a repeat unit of 2 carbons, but now one of those carbons has a chlorine dangling off of it. Here, because the monomer, there's actually a space between those, even though it's a little hard to say for sure. Vinyl chloride is 2 words, so when we make the polymer name, we're going to have to put parentheses around it. Okay, so PVC is what we're making there. I guess one other thing that's kind of an interesting side note is polyethylene actually comes in 2 varieties, high density polyethylene, or HDPE, and low density polyethylene, or LDPE. The difference between them is just like high density polyethylene really is like exactly what we've shown here, with the chain just being like a straight thing of CH2s with no weird stuff going on. Turns out if you do this radical reaction, it doesn't quite work smoothly for polyethylene because at some point, once you get a long enough chain, this thing can actually whip around, rip an H off of itself a few carbons back, and then create a radical back here, and then it'll start polymerizing from there. So you get these chains with all these weird branchy units sticking off of them, and then they don't pack together as nicely, and they're lower density. So that's how you get LDPE, which is used for like shopping bags and stuff like that. It's not as strong as HDPE, which I think is used for like milk cartons and plastic jugs. A question?
So is it wrong to say like ethene and polyethylene?
Oh, no, that's totally fine. Yeah, use either IUPAC or common names for them. It's just like when people started making the polymer names, they were using like old pre-IUPAC names before, for the monomers they're using. Yeah. Okay, a question?
How do you know, like, for example, with the polystyrene polymer,
Mhm.
rewrite those, like, where to choose?
Where, what now? Sorry, where the chain builds? Oh, good question.
Like, how do you know that vinyl chloride looks like that as a polymer?
So pretty much what you want to do is drawing polymer structures. You pretty much just want to take the alkene, erase the pi bond, because we're getting rid of that, and then draw a new bond to the repeat units that's going to go in on either side. So, yeah, and then draw parentheses around that because that's going to be your repeat structure inside the parentheses right there. And then if you want, you can redraw it kind of more nicely than I have here. Or you can redraw it when it's the monomer in the first place and avoid having to do that.
And does the chain build on both sides, or how do you know which side builds?
So it's always going to build out from the initiator. So if we're looking at, say, PVC, okay, so we have this monomer going on. I guess we have sort of the same kind of choice making that we have to do when we were looking at radical HBr addition, which is one of these carbons is going to get the new bond to the radical, and one's going to get stuck holding a dot of its own. And then the question is, which side is better equipped to hold the dot? And so this is kind of where Markovnikov's rule, or this is where like more stable radicals are more substituted kind of comes in. So say we do it this way, we're going to end up with this radical versus if we do it at the other end, if we do a radical there. Between the two, I think the chlorine is actually going to be more stable. We haven't really covered, like, we've only covered whether more R groups are going to stabilize carbocations and radicals. Turns out chlorine has sort of like, it's fighting its own effects, where like it has lone pairs that it can contribute, but also it's electronegative. So it's a bit of a toss-up for this particular monomer. But if we had something with like just a regular R group, or for instance, a phenyl ring, an aromatic ring hanging off of it, then it's a lot more clear-cut. Then we definitely want the radical at the place where the extra R group's attached, if that makes sense. Mm-hmm.
So when we're making these polymers, is it possible to have either one of those happen at any point in the chain, since it can happen millions of times?
Yeah. So a lot of this is governed by statistics, and so you might have what's called like head to tail or tail to tail connections, kind of, where like you might have like most of the units polymerize with the dot going on like the more substituted carbon, and then occasionally like a wrong way one will get thrown in the chain there too. Yeah, so it's not really following like exactly the same connectivity anytime. It's a lot of it is just like how did things happen to pan out when you were sticking them together. Mm-hmm. Okay, so there's a whole lot more in this field that I'm probably going to gloss over for the time being, but that's just kind of an intro if you're interested. Okay. So to wrap up this chapter, I'm just going to sort of do a list of the reactions that we've covered in a way that, whoops, in a way that will hopefully sort of make it easier to keep them straight. Because once we start stringing reactions together later on, having like a consistent way to keep track of what does what is going to be kind of helpful. Okay, so I'm going to break it down by what groups get added to the molecule. So I'm going to do reactions that add 2 non-H groups. These are going to be the ones that we covered at the start of chapter 5, the ones that make the bromonium ring, pretty much, or all the ones that we've covered. So dihalogenation and halohydrin or haloether formation. Okay, so all 3 of the ones in this category I'll go by the bromonium, or I guess more generally the halonium ring, but bromine is most commonly used. Okay. So they're all more or less the same reaction with a few little details that are different. The biggest category are reactions that add 1 H and 1 non-H, because here is where Markovnikov actually has something to say about it. Note that even though the ones in this first category have like sometimes a set regiochemistry, like they might have bromine adds here, oxygen adds there, it's not Markovnikov or anti-Markovnikov in this category, because Markovnikov specifically says H adds here, non-H adds there. So it only applies for here. So only place where Markovnikov versus anti-Markovnikov applies. So in Markovnikov style, we're going to see HX addition, or we did see HX addition in chapter 4. Acid catalyzed hydration. Or in other words, just adding H3O plus or equivalent to the molecule. And then the third one we saw in this category is oxymercuration reduction. Okay, so all 3 of those add Markovnikov style. Mechanism is more similar for the first 2 than it is for the third. The first 2 go by carbocations, so you got to watch for rearrangements. Okay. And then we also saw some examples of the opposite of this, which is anti-Markovnikov. So that's going to be hydroboration oxidation. And radical HBr addition. Okay. Don't have to worry about carbocation rearrangements for either of those because they don't go by carbocations. Okay, so that's pretty much it. In both the Markovnikov and the anti-Markovnikov categories, we have at least one way to add an H and a halogen, and at least one way to add an H and an OH. So this is going to be pretty useful later on. when we start looking at swapping those groups out at will. Okay. Third category, we've seen adding two non-H's. We've seen adding an H and a non-H. Kind of makes sense the third category is going to be adding two H's. Okay, so there's pretty much only one possible way to set this up. It's hydrogenation. Okay, so we're adding two H's, one to each carbon of the alkene. Okay, and then finally, the kind of weird outcome that we saw is, or the one like odd reaction out for this chapter, is reactions that break the CC bond entirely. And that's ozonolysis. Okay, so I guess if you wanted, you could add a fifth category, and that's reactions that make polymers, which we sort of covered here. But I'm not going to include that in this list because these are the ones that are going to be useful for like chaining multiple reactions together when we do synthesis. Polymerization is just kind of an interesting side note, but we're not going to really, I guess, use it for further kind of reactions as we move on. But keeping all these reactions kind of organized this way is going to be super helpful later on. So if you're looking at these and you're like, I don't recognize that name at all, this is a good sort of, I guess, summary sheet to go back and review if you're feeling kind of weak on any of these reactions. Okay, questions about any of that? Okay, cool. So that wraps it up for chapter 5. That's all the reactions of alkenes that we're going to see for the time being. So the last couple of chapters have been real like mechanism and reaction heavy. What we're going to do now as we get into chapter 6, which by the way, I did not yet post the notes for, so I'm going to get to that later today, sorry. We're going to sort of take a step back from bombarding you with reactions for a little bit and spend a while looking at geometry. So if geometry comes really easy to you, this chapter and the next chapter are probably going to be kind of a cakewalk. If visualizing three-dimensional stuff is a little trickier, then this might be sort of a little bit more intensive for you. Okay. So, chapter 6 is stereochemistry. Okay, so we've actually already seen one example of stereochemistry. So we've seen a type of stereoisomers. And if you remember when we introduced these in chapter 4, or when Garrett covered them, these are things with the same connectivity, but different three-dimensional shape. So cis-trans, or EAZ more generally, alkenes are one example of stereoisomers. Because everything's connected to the same atoms if you've got like the E versus the Z alkene, but they're still not the same molecule. Like bits are pointing in opposite directions from where they are on different molecules. Okay. So we're going to look at sort of a more generalized coverage of stereochemistry and some different ways we can have that happen in this chapter. I guess just a quick review, a quick reminder here, if you don't have a model kit, like get one or borrow one if you're having a hard time visualizing this, because it really does sometimes make the difference between being able to understand this and not. Okay, so before we get into this, kind of a quick review of drawing tetrahedral geometry real quick, because this is important. Okay, so usually what we're going to show for tetrahedral carbon, we're going to show 2 bonds in plane, 1 bond in front and 1 bond behind the plane. Okay, so the most common way that you're going to see is something like 2 bonds in plane, 1 bond in front as a bold bond, and 1 bond behind as a dashed bond. So bold or wedged bonds are coming out towards you, dashed are going away, as a reminder there. Because this is tetrahedral, technically your view of the dashed whatever is out at the end of this bond should actually be blocked directly by your view of the bold bond. If you remember Newman projections, technically these two are eclipsing each other, or they would be if they were on separate atoms and we're looking at the rotational thing going on there. So what we're going to do is just like skew it just a little bit to one side or the other so that we can actually see both the atoms on there. But splaying them out this direction where bold goes slightly to the left is really the same molecule or the same thing as splaying them out a little bit so the bold goes off to the right. Really for perfect tetrahedron, they shouldn't be splayed out either direction, but then we couldn't see what was going on. So we're just going to tweak it just a little bit here. Okay. So that's kind of the most common way you're going to see is 2 in plane, 1 wedge, 1 dash. Occasionally you'll also see and actually, sorry, actually, yeah, I'll do this first and then I'll go back and show some wrong ways to draw it. So you might also see 3 that are pretty close to in plane. And then 1 forward or back. This is a little bit less accurate because if this is a tetrahedron, what we're really showing here is, I'm glad I brought models. So one's coming out towards you, say this yellow one here, and we're showing 3, sarcasm finger quotes, in plane. So like the purple, purple, and green that I have here, they're not exactly in plane, but they're close-ish, and so people will often show them this way. Usually this only shows up if you're looking at some sort of structure where you've got multiple rings together and you don't want to show like any of the rings popping out of plane. But this is to be avoided if you possibly can. Because really what people mean when they draw it like this is there's 3 going slightly away from you and 1 coming out towards you, which is how this actually looks, this tetrahedron, when you're viewing it like yellow coming out towards you. Okay, or you could do it the other way around where the yellow is going away, and in which case the other 3 would still be drawn in plane even though then all 3 are slightly coming out towards you. Okay, I'm going to take a minute to erase the board unless people have any questions about that part so far. Okay, cool. Give me just 1 second here. Okay, so one thing that you do want to avoid when you're doing this, if you're showing two in plane, then you have to do the bold and the dash on the outside of the angle that they make. Okay, so what I mean is that this is good. This is bad. There's no way you can ever get something with tetrahedral geometry lined up to where it's got two bonds in plane from your point of view. Say like green and purple here are in plane, and then like red is going away, yellow is coming towards. There's no way you can ever get it so that green and purple stay in plane and then like one's above and one's below your viewing angle. This is not tetrahedral geometry. And if you try to apply any of the stuff we're covering in this chapter to something that's being drawn like this, you're going to get nonsense answers out of it. And then obviously something like this is even worse. And also watch out for, I do sometimes see people put like two bold things or two dash things. That's also not tetrahedral geometry. So pretty much if you're doing the two in plane, which is going to be like, probably should be your default unless we see one of the cases where it makes more sense to draw it the other way, just draw two in plane and then make sure the others are on the outside of the angle, one bold, one dashed. Okay, questions about that? Okay, cool. So what we're going to be looking at in this chapter is kind of a weird quirk of us living in a three-dimensional universe and carbon having tetrahedral geometry. We're going to be looking at enantiomers. Okay, so the whole idea here is that some molecules are identical to their mirror images and some are not. So if I have, say, this molecule here, and let me actually draw. All right, we're going to use a lot of big dotted lines to indicate mirrors in this chapter because a lot of this has to do with reflection across a hypothetical mirror plane. So if I show this molecule here, OH, CH3, and then H and H, I could draw the mirror image where like the OH is still up, CH3 is sticking towards the mirror, and then this bold H reflects into that bold H, and this dashed H reflects into this dashed H. So imagine there's just like this big mirror plane just sort of like sticking out of the board, and this molecule is looking at itself in the mirror. This is the reflection that it sees, its mirror self. So if I use purple for H's here, here's how this is looking. So purple are my H's. They're sort of coming towards you and going away from you. OH is my yellow. It's sticking upwards. And then methyl, the CH3, is my green. That's sticking in towards the mirror. The mirror image of that is, again, OH up, CH3 towards the mirror, H front, H back. So you'll notice that I didn't actually have to change the molecule at all. All I did was spin it around. It's the same thing whether it's on this side of the mirror or that side of the mirror. So this one is identical to its mirror image. All I have to do is move it around and it looks the same as it does in the mirror. So this one is identical to its mirror image. If I want to change that, all I have to do is set this molecule up so instead of having two copies of the same group on it, I have 4 different groups coming off the same carbon. So again, I'm going to draw a mirror, and how do I have this in the notes? Okay, I've got an OH up, still got CH3 towards the mirror, only now I changed it so I have H dashed and BR bold. So again, OH here, CH3 towards the mirror, bold BR, and dashed H. Okay, so what I'm going to do is swap out that purple for red. Okay, so this one is this one actually. Okay, so I'm using red for bromine. Kind of makes sense, bromine is a reddish liquid. Okay, so OH is up, methyl is still sticking towards the mirror, H is in back, and bromine is coming out towards you. And then here, OH is up, CH3 is towards the mirror, bromine's coming out towards you, and H is in back. So you guys can see that these are two mirror images of the same thing, right? But if I try to like turn these into the same molecule, I'm going to run into a problem. If I try to superimpose these, I can get the two OHs to line up, I can get the two methyls to line up, but I'm trying to get an H and a Br to be the same, and an H and a Br to overlap over here, and that's never going to happen. And no matter like how I twist and turn these things, I'm always going to have a mismatch where like two of the groups will line up fine at least, and then the other two just won't match. So these two are not the same as their mirror images. These two are non-superimposable mirror images. So superimposable basically means you can do what I was trying to just do and like overlap them with each other and have everything match up. And another name for non-superimposable mirror images is enantiomers. So that's what we mean when we say enantiomers. That's a good stopping point, so I'm going to pick up here next time.